Okay, let's continue to the second half of chapter 6. In this part, we will discuss transmission line discontinuities. This transmission line terminated with reactive load and line with initial conditions. So here is a common theme structure in transmission lines, that is a junction between two transmission lines of different characteristics. So as the figure suggests, you have one line to the left, which is labeled with Z sub 01, and its propagation velocity is Vp1, and the right hand side is another line, and its characteristic impeller is Z sub 02, and the velocity is Vp2. So, of course, because the characteristic impedance of the two lines are different, so the incident wave, which is the this arrow that represents the so-called incident signal, and the needle arrives at the junction, that is the interface between the two kinds of transmission line, due to the difference in the characteristic impedance. That is, Z sub 01 is not the same as Z sub 02. It will set up a reflected part, reflected wave. So it's labeled as the minus sign, and its propagating direction is to the left. And at the same time, the incidence will introduce some another term which is referred to as the transmitted part, transmission. So incidence, reflection, and transmission. The transmission is labeled as double plus, meaning that the components the part of the energy, the part of the signal that continues its propagation to the right into the second transmission line. Alright, and the production, the growth of reflected wave and the transmitted wave is aimed to satisfy the boundary condition, which are, what are the boundary conditions? The voltage and the currents, according to the circuit's law. The voltage on the two sides should be the same, and the total currents that goes into and goes out of the node should be the same. So using the boundary condition, we can write up related equations at the interface. So in the middle, 所以这个虚线称之为什么？界面嘛，传输线的界面，所以有前段跟后段。那为了要让这一个界面上的总电压保持一致，所以你这边看到的是 V 正加 V 负，然后这边是 V 正正，所以这两个电压要相同。那这边的 I 正加 I 负要等于 I 正正，但是要小心哦，这个电流的方向是往右边为正，所以实际上你的 I 负是往左边跑的，实际上的 I 负是往左边传播的，所以在正负号上面要稍微想清楚一点，那就像我刚刚讲的，这三个成分叫做入射、反射跟透射，incidence, reflection, and transmission. Now, in this slide, we introduce another idea that the second transmission line can be equivalent to a load. If the second transmission line, the line to the right, is largely lossless. If there is no apparent loss mechanism reside within the second transmission line, it can be equivalent to as a resistive load. And from the perspective of the first transmission line, the reflection property should be the same as long as the equivalent termination, the impedance of the equivalent termination of the equivalent resistor is the same as the characteristic impedance of the second transmission line. The reflection produced at the interface is the same as the one produced by the termination. So it's okay to use a load of the same characteristic impedance to represent the follow-up transmission line circuit. Okay, so let's take a look at the so-called boundary condition. So the first one is the total voltage should be the same, and the total current should be the same as well. So you have V plus V minus equals to V double plus. And the current I plus plus I minus equals to I double plus. And we also know that according to the characteristic impedance of the transmission line and the propagating direction, you can replace I plus with V plus over Z sub 01. I minus equals to minus of V minus over Z sub 01. So you need to note that there is a sign difference for the I plus and I minus part. And I double plus, which goes to the right, can be replaced with V double plus over Z sub 02. So equation 6.41b can be substituted with this equivalence as V plus over Z sub 01 minus V minus over Z sub 01 equals to V double plus over Z sub 02. Then the two equations, that is the 41a and 42, can be used conjunctionally to solve for important to solve for some important properties of this equation, which well, so in the two equations, what are the known property? Z sub 01, Z sub 02, the characteristic impedance of the two lines are known. The incidence V plus is known as well. The unknowns are V minus and V double plus. Okay, the reflected voltage and the transmitted voltage are unknown. And thankfully that we have two equations, so they can be solved for sure. And the first thing that is helpful in solving the problem is use the representation of what is this? Gamma. What is gamma? Reflection coefficient. Reflection coefficient. Remember last week when we talked about the reflection coefficient of a transmission line terminated with a low resistance RL. The reflection coefficient, which is defined as V plus over V minus, equals to what? Equals to RL minus Z sub 0 over RL plus Z sub 0. The reflection coefficient definition is the same here. And the formulation of the reflection coefficient is the same as well. So again, you take the first term on the denominator is what? Is the characteristic impedance that you are looking into from your propagation point, from your propagation direction. The characteristic impedance on the other side, that is Z sub 02 in this case, minus the characteristic impedance from the incident side, that is Z sub 01, over Z sub 02 plus Z sub 01. Okay? I bet that you should have already memorized the definition of the reflection coefficient. Okay? 要记起来啊，再讲一次啊！你要是考试的时候连这个都没记起来的话，那就都没有数了哈。OK， 好，所以看过去的那个特性阻抗，扣掉自己这边的特性阻抗，好不好？反射系数的那个电压反射系数的表示式，请你好好记起来。OK， 好，所以在这一个状况底下，就是 Z02 减去 Z01 over Z02 加 Z01 嘛，好。 in this slide, we introduce another new parameter that is the so-called transmission coefficient. And as the name suggests, you can imagine it's closely related to the reflection coefficient. And in fact, the transmission coefficient can be expressed in terms of the reflection coefficient. So here's the expression, which is shown here, and it's not that difficult to memorize. Okay, so I recommend you to memorize this formulation right now. The transmission coefficient, which is usually expressed in terms of tau. Well, that is another Greek letter, all right? Lowercase Greek letter tau. Tau equals to 1 plus gamma. Tau equals to 1 plus gamma. So if you, it should be easier to memorize the definition of the transmission equation, which is what? Which is V double plus over V plus. Okay, so we are expressing the transmission coefficient in terms of voltage. So that will be the transmitted voltage V double plus over the incident voltage V plus. And remember that our first boundary condition at the interface is the voltage on the two sides should be the same. So V plus plus V minus equals to the V double plus. All right? So you can substitute this into the denominator of this expression. So you have a V plus plus V minus over V plus. And you can recognize that the first term equals to 1, and the second term is V minus over V plus, which is what? Which is the definition of the reflection coefficient. So 6.44 is the definition of the transmission coefficient. So tau equals to 1 plus gamma. And down below is the definition of current transmission coefficient. Again, I would suggest you to skip this part, all right? And because it may confuse you, okay, but the voltage transmission coefficient and the voltage reflection coefficient is enough, sufficient for you to solve for transmission line junction problems. Okay, so we just need to memorize the transmission and reflection coefficient in terms of voltage. Okay, and again, let's examine the transmission in terms of power. So what is the significance of P double plus? Okay, P plus is the incident power. So P minus is reflected power. And the P double plus will be the transmitted power. Okay? And of course, the power can be expressed in terms of the product of voltage and current. So V double plus equals to P double plus equals to V double plus times I double plus, okay? And V double plus can be expressed as V plus times 1 plus gamma, the reflection coefficient, and I double plus, okay? So that is the current transmission coefficient that we skip in, that you can find in the previous slide, can be expressed as I plus times 1 minus gamma. And I plus can be replaced with V plus over Z sub 0. Oh, okay, we didn't do the substitution here. Okay, but anyway, you can identify that in the right-hand side of the equation, you have a V plus and I plus, and the product of the two is what? Is P plus, the incident power. So V plus I plus is replaced with P plus. And the product of 1 minus gamma and 1 plus gamma equals to 1 minus gamma to the square. So we have this expression. What is the limit of the reflection coefficient? We have discussed that last week. Have you Does that have you recorded anything about the limit, the magnitude about the gamma? Gamma 的大小限制在哪里？好，我们上礼拜有讲嘛，gamma 的大小最大为1，它是介于它的大小，它的 magnitude 介于0到1之间。对于被动电路来说，对于被动元件、被动电路来说，在没有主动元件的状况底下，什么叫主动元件？有插电的、有吃电的叫主动元件，好不好？简单讲，不需要插电、不需要吃电的就是被动元件了，要插电的是主动元件。那在我们目前所讨论的微波电路里头，我们没有讨论到放大器这种主动元件，所以我们现在讲的是被动元件。对于被动元件来讲，被动的微波电路来讲，它的反射系数的大小会落在0到1之间。所以伽马平方，当然伽马它本身可以是实数或者是虚数，所以它可以是负1到1之间的实数，也有可能是 magnitude 小于1的任何的复数 complex number。但这些条件在取伽马的平方之后，伽马平方的值会落在哪里？会落在0到1之间。OK， 会落在0到1之间。所以1减伽马平方的结果会是什么？会是一个小于1的数值。假如你的伽马平方是一个 magnitude 的话，那这一个小括弧里头的1减伽马平方，那会是一个小于1的数值，但是大于0。所以这个东西的意思是什么？这个东西的意思是，你传输线左边打进来一个 P plus 的能量，然后有部分能量可以穿透变成 P double plus， 但是它的大小只会是你 P plus 的最多跟 P plus 一样。假如你是一个 matching 没有不连续的状况底下，假如是 matching 没有不连续的话，伽马等于多少？等于0嘛。你是一个 matching 的一个 transmission line， 有达到所谓的阻抗匹配的话，伽马等于0，没有反射，所以所有的 power， 所有的能量都可以 deliver 到下一段去。所以在微波电路的设计上，一般来说，我们会去想要让 available 的 power、available 的 signal 尽量能够 deliver 到 following stage。在没有放大器的状况底下，所以要做到这件事情，你就要想办法解决掉伽马，把伽马降到越小越好，甚至是0。0的话就是所谓的匹配的状况。这样子的话，不然的话，随着你的电路越复杂，越来越多段，越来越多元件插在里头，只要每一个这个 1 minus gamma to the square 都比1小的话，那结果是什么？你讯号就越来越弱，你的 available power 就越来越小。所以我们这边谈的是电路设计上面的一个基本原则了那可以从这个 available power 的这个 perspective 来去检视它。OK， so from this equation we know that for passive transmission line component or passive circuit，the available power is no greater than the incident power. You can only get a fraction of what is available for your following stage in terms of the transmitted power. Alright, and here we would like to look into the two transmission line case in terms of an example using the bouncing diagram technique. So in this case, we actually have a more complicated transmission line circuit. So here we have 3 sections. The one to the left, labeled as line 1, has a characteristic impedance of 50 ohm. Its length is of 2 microseconds for signal propagation. In the middle is line 2, which has a higher characteristic impedance of 100 ohm, and its propagation delay is 2 microseconds as well. The third line, the characteristic impedance is 50 ohm, and the propagation delay is 2 microsecond Q. To the left is the source part. The source is what? Well, the source is the so-called impulse source, which is represented as with a delta function. So what is the significance of delta function? 公数有学过吧？有吧？哈 ，OK， 好。我听马老师讲说，你们高中的时候没有学，只有学过 sin、cosine 跟 tangent， 没有学过 cosine 跟 secant 跟 cotangent 吗？是这样吗？啊，有听过 secant cosecant function 吗？有哈 ，OK， 好了，我相信你们这么优秀，应该有听过吧？哈 ，OK， 好，所以 delta function 哈，就是什么？你可以假设它的大小为1，但是它存在的时间非常短。存在的时间非常短，代表什么物理意义？存在时间非常短代表它的能量分布在整个频谱上面都有。你有学过 Fourier transform 吗？有没有？因为学过 time domain 跟 frequency domain 的 Fourier transform 嘛，所以回想一下 Fourier transform 的最简单的物理意义是什么？假如你有一个在 time domain 上面无限延伸的函数，那么它在 frequency domain 上就会聚集在单一的频率，例如 sinusoidal function、sine 啊、cosine 函数单一频率的函数。那它在时域上面就是一个无限延伸的函数。那反过来讲，只要你在时间上面很集中，就啪，像是打雷啊，或者是核爆。核子爆炸，它在很短的时间里头释放很多的能量，这些能量就会在频谱上面，所有频谱都涵盖，所有频谱都有能量的分布。所以所谓的 impulse 的话，它其实，当然我们这个例题里头没有讲那么深啦，没有讨论到那么深。但你看到 delta function， 看到所谓的脉冲讯号，你要知道是它代表的是能量在频谱上面分布是很广的。OK. Alright, so to the left hand side we have the delta signal, an impulse source, and the internal resistance of the source is 50 ohm, which is the same as the characteristic impedance of line 1. So it's a matching case. So you have a match impedance. And to the right is the termination, which is a 50 ohm termination. Again, it's the same as the characteristic impedance of line 3. So the derivation or the derivation of the bouncing diagram is simplified because of the matching node. So there are no reflection as the signal goes to the right end or goes to the left end because the match load absorb all the incident power. All right. Okay, so let's begin with the bouncing diagram of this example 6.3. So the source is referred to as the unit impulse source. So the magnitude is 1, and the duration of the source signal is infinitely small, infinitesimal. 时间在时域上面存在很短，大小为1，所以称之为 unit impulse source. So before we proceed for the formulation of the bouncing diagram, we need to calculate some basic parameters of the line. That is this part. the reflection coefficient at the interface. Okay? So here is the reflection coefficient and transmission from looking from section 1 to section 2. So the gamma is what? 反射系数。对，从 section 有的时候我们会这样写啊 ，gamma 1 2， 意思是从 section 1看到 section 2。写这样子的话 ，1 2其实比较方便，你在这边写那些数字。所以从1看到2的话，这边要放多少？100嘛，对不对呢？减50，100加50。所以 gamma 1 2 the reflection coefficient at the first interface is 1/3. What is the corresponding transmission equation? Well, using the formulation of 1 plus gamma, so it's 4/3, right? Note that if you invert the direction of incidence and transmission, say you're looking from section 2 to section 1, what is the reflection coefficient? It will become 50 minus 100 over 150. So it's a minus 1/3, all right? And how about the corresponding transmission coefficient of tau 1 to 1? Again, 1 plus gamma, so it's 2/3. Okay? And you can do the same for the second interface, which looking from section 2 to section 3, and the corresponding characteristic impedance are 150. So gamma is minus 1/3, tau is 2/3. Okay? And the reflection coefficient at the right hand, which you have match termination, the reflection coefficient is what? Is 0. And so is the signal goes into the source. So the reflection coefficient on the left-hand side is 0 as well. So before proceed the drawing of the bouncing diagram, you need to calculate corresponding reflection and transmission coefficient at the interface and termination, right? So the first question here is, what is the time delay required for the signal goes from the source to the load? So for the signal, so according to the bouncing diagram, part of the energy goes from the signal starting from the left-hand side, starting from the impulse source, and it goes to the 1-2 interface and goes to the 2-1-2-3 interface and reach to the right end. And because the length, the propagation delay of the 3 sections are 2 microseconds each, so the time required for the first signal to reach the right-hand side, reach the termination, shall be 6 microseconds. Okay? How about the magnitude? Well, you need to proceed for some calculation. First is try to figure out the incident signal originating from the source using the voltage division law, 电压分压定理了哈，因为你最左边的话，你看到的是什么？最左边是50欧姆的内电阻配上50欧姆的 section 1的特性阻抗啊，所以它的初始的那个电压大小是50加50%嘛，好，然后 source 的电压大小是1伏，所以是1乘上1/2。接下来乘上什么 ？B plus equals 0.5， and then the signal that reach to the section 2 shall be V plus times tau 1 2. That would be V double plus in section 2. And how about the component that goes into section 3? It shall be equals to the product of V2 double plus times tau 23. Okay? So you need to do the product of tau 12 and tau 23. So in this expression, you have, this is in fact tau 12, and this part is tau 23. All right? And check out with this value. We have the product of 4 over 3 and 2 over 3. So 1 times 1 over 2 times 4 over 3 times 2 over 3, you end up with 4 over 9. So the first signal that reaches to the right-hand side at the terminating resistor has a voltage of 4 over 9. What about the duration of this signal?你的 source 是一个 impulse 嘛，是一个脉冲嘛，所以第一个抵达到右边的那个讯号，它也是一个脉冲，所以我们在 bouncing diagram 上面就画一个箭头啊，那箭头的长度可以代表它的大小，但箭头的意思表示它存在的时间就一下下而已 ，OK， 哦，那既然有第一个到达的，那这个图你看起来你还看到什么？还有第二个到达，还有第三个到达嘛，对不对？啊，只是第二个到达跟第三个到达的像会有什么特性？啊，所以从这边的话，你大概就可以画得出来了哈。So the figure of merit of the bouncing diagram is help you to understand what's going on within the transmission line. You have if you have impulse source, like example sequence C, the signal will generate transmission and reflection at the interface. And the transmitted or reflected signal may produce follow-up transmitted and reflected signal. So as you can trace the bouncing diagram to identify fundamental and higher order terms that may come to the right-hand side and the left-hand side of the transmission line. So for example, the first signal that reaches the right-hand side arrives at the time instant of 6 microseconds, and the magnitude as we have already calculated, is 4 over 9. The second impulse that reaches to the right shall follow this path. Okay, so it's a pass through interface 1 to 2 and get reflected at the 2-3 interface, and then get reflected again at the 2-1 interface, and then transmitted through the 2-3 interface. So the propagation delay accumulated in this pass, in the second pass, will go through the transmission line 5 times. There are 2 additional propagation. So the total time required for the second impulse that reaches to the right shall be 10 microseconds. How about the magnitude? Comparing to the first pass, here you experience a reflection, which has a reflection coefficient of -1 over 3. And here you will experience another reflection, which has a coefficient of 1 over 3 as well. And the rest are the same as the first pass. This is tau 12, this is tau 23. The difference for the second part is this and this. There are -1 over 9, I'm sorry, -1 over 3 and -1 over 3 as over here. So the product of the 2 reflection coefficient is what? Is 1 over 9. So the magnitude of the second impulse shall equals to 4 over 9 times 1 over 9. So it's expressed as 4/9 to the square. So it's actually 4/81, right? How about the third one? The third one will need another 4 microseconds to reach to the right-hand side because you need to get the 2 additional propagation delay should be accounted for the third term. And for the 2 terms, you will accumulate another 2 reflection. That is -1/3 times -1/3. Again, the product of the 2 reflection is 1/9. So the third term will be 4/9 to the cube. So it's再乘一个9是多少？7×9=4。All right. Well, you can do the rest. Okay, so how about the other side? The first term that comes back to the source side will be the reflection at the 1-2 interface. All right, so what is the propagation delay needed? 4 microseconds, right? How about this one? So you can trace the path, that will be 8 microseconds. How about the third one? That will be another 4 microseconds, so it's 12 microseconds. You can calculate the magnitude, so that will be 1/2 times the reflection coefficient is 1/3, so that would be 1/6 for this part. And this part you need to times 4/3 and what? And -1/3 and the transmission coefficient 2/3 over here. Well, you can do the calculation, all right. So it's just a series. So no matter you are calculating the signal that reaches to the right or reaches to the left, you can express length in terms of an infinite series. So here's the output voltage signal. Equation 6.47 is the output voltage signal expressed in terms of an infinite series on the so as you can see, there are summation of delta function with different time delay. So the first term comes with a time delay of 6 microseconds, the second term comes with 10, and the third one comes with 14 microseconds. And the magnitude are different as well. Have you noticed that the magnitude are getting smaller and smaller? Why? Well, because the available power for a delta signal for the impulse is limited. And you have a 2 resistor on the 2 sides. So as the signal reaches to a right hand or right end or the left end, the incident signal are absorbed by the resistors. So as the time progresses, there are fewer and fewer energies reside on the transmission line. So as a result, the higher order terms which reside within the transmission line are becoming smaller and smaller. 好，简单讲就是，因为你的脉冲讯号它只存在一个有限的时间，所以它能够提供的能量是有限的。而这个传输线的左端跟右端都是电阻式的负载，电阻是会吃能量的。所以你越早到达那些左端跟右端呢，它的能量就会被吸掉。所以在传输线上面，剩下的能量就会随着时间的推移而怎样越来越少。所以你的高阶相，你是在那边弹的比较多的，它的那个能量的比例就会越来越小，越来越小。 好，而且你的反射系数刚才能看到，它的 magnitude 都是小于1的，啊，所以高阶相它就是会越来越小，越来越小。OK。Alright, so you can write up this evenly series, 6.47. Supposing that the source is an impulse source. And if you can follow the textbook to collect some common terms, because T1 equals to T2 equals to T3, so the sum of the T1, T2, and T3 is termed as T sub 0, which affects 3 times of T2. And you can identify that higher order terms will accumulate 2 times of T2 as it bouncing back and forth in the middle. So equation 6.48 try to express this equation more organizedly, with T minus 2 and T2 minus T sub 0. 现在在铺梗了，我们看一下那个梗是怎么铺的。这边讲到就是说我们这边讲的刚刚已经的 6.3 它是一个脉冲讯号。为什么？因为脉冲讯号容易辨别，容易辨识，所以你会看到它那个弹来弹去，它的那个现象传播或者到达终端的现象是清楚的，是看得到的。但是呢，这个脉冲讯号的，毕竟在真实的通讯系统里头，我们不是那么常看到脉冲讯号，我们常看到的是这边所讲的正弦波讯号，所以我们接下来要做的是把刚刚的那个 response 换成正弦波的 response，because the unit impulse response of the system is a series of impulse delayed by time, the response of any other excitation can be found as the superposition of the time function obtained by delaying the exciting function and multiplying by appropriate constant. So, as a result, we can directly replace the source as a continuous source, such as cosine omega t, that's a sinusoidal source. We can simply replace delta t as cosine omega t. That becomes the time domain response of a sinusoidal input signal. So the things here is simply replace delta function as a sinusoidal function with appropriate description about the time delay within the function. So it becomes cosine omega times this. That will be t minus 2n t2 over minus t sub 0. So here we use the superposition law to substitute impulse function with sinusoidal function, which is more used often in actual communication system. Alright, and the next thing, 所以接下来的事情很重要大概就是这一章的精华了在这一个式子上面。所以我就直接切中文讲了这一个式子你要注意它直接把它从 time domain 换到 frequency domain 了有没有看到 6.49 的式子里头，这个是一个 time domain 的 description， 它是 VRO， 这个是 O 啦 ，output 的意思啦你的 output voltage expressed in terms of time domain function。但是在这里第一个啦，他先做的事情是把这一个 cosine signal 的 expression 把它写成 phasor。因为 phasor 的 expression 里头是把 cosine omega t 换成 exponential j omega t， 把它换成 exponential j omega t 嘛。你看到原本的式子里头有 omega， 那是频率的描述 ，t 是时间的描述，所以我们把它换成 exponential j omega t，OK？然后因为是 phasor， 所以我们又把 t 给偷偷拿掉了。把一些 exponential 真的这个 exponential j omega t 又不把它写出来，我们只留它剩余的那个 负的 minus j omega 2nt2 加 t0，那个 exponential j omega t 因为是非色，所以把它拿掉。那拿掉之后，你就发现这个式子里头变成它的变数，它的 variable 变成是 omega， 所以这一个函数就变成 v out of omega。Which means if you change the frequency, you can find the corresponding response of this frequency. So you can substitute in any frequency, any omega, and that will be the result of the frequency domain response. And because this is an infinite series with 它是一个等比级数了那个等比的那个比是多少？1/9吧，是1/9。所以无穷等比级数它的解析解是可以得到的嘛，就你在国中、高中的时候背的嘛，1减α1/1嘛，所以重点在于你这一个等比的那个相次。所以这个等比的相次，完整的等比相次是这个 1/9 乘上 exponential minus j2 times omega t2。所以可以写在这里。那个 common 的共通项被提在分子 exponential minus j omega t0。那这是那个等比级数的那个东西。而这个式子你看到这里头没有那个小 t 它只剩下 omega。所以利用这一招，它把传输线的 time domain response 转换成 frequency domain response， 有没有？好，那么以后我们在第7章开始在讨论传输线的特性的时候，我们都是用 frequency domain response。好，所以这边这一页这一页第15页是第6章的一个你一定要想办法去理解的一个东西了用这个式子来去推导出传输线系统的 frequency response。好不好 ？Okay. We probably do not have time for follow-up discussion about the frequency response of thing, and well, I probably will postpone the